Everyone for joining us for this second session. I'm really sorry I can't be there. I had to have some surgery in November and I can't fly until February. But those of you who saw me in Japan, I can now walk without a stick, so a big improvement. Let's start off with our agenda for this session. So we'll be starting off with me talking about our cloud and high performance systems. Then Keon Kim from KISTI on research platform for multi-domain issues. Then Jianhui Zhang from NSCC in China. Nora Silla presented in the last session. And then Yana Maka from Rian's. Hopefully we'll get to you a bit earlier, Yana, seeing I know your time zone's even worse than mine at the moment. And then we'll finish off with Werachai from Thailand. So without further ado, thank you very much for joining us. And can I make this actually work? Okay, so I'm Andrew Howard, Associate Director, Cloud Services and Innovation at the National Computational Infrastructure at the Australian National University in Canberra. I'd like to talk to you today, giving you a brief introduction to NCI, and then some updates in terms of our new cloud hardware, Kubernetes environments, and Gen 3 and genomics projects that we're working on with some of our New Zealand colleagues as well to deliver a project called Guardians, which is a genomics research platform for Australian and New Zealand researchers. So let's start with what NCI does. We're one of Australia's two high-performance computing services. We provide a comprehensive vertically integrated research service, providing national resources which are merit-driven based on research objectives. We operate as a formal collaboration between the Australian National University, the CSIRO, the Commonwealth Scientific, Industrial and Research Organisation, which is our government research initiative, the Australian Bureau of Meteorology, and Geoscience Australia. We're a partnership of research-intensive universities supported by funding from the Australian Research Council. We're directly funded through the Department of Education, Skills and Employment's National Collaborative Research Infrastructure Strategy Project. Currently, there is a new NCRIS round in operation. We received 55 million in the initial round, and we're currently waiting for funding confirmation for additional funding to upgrade our Gardi supercomputer system. So for those of you who are not familiar with Australia, NCI is located on the right-hand side or the east coast, and our sister centre, Pawsey, the other Tier 1 facility in Australia, is located over in Perth on the west-hand side. We're connected by multiple 100 gig connections, supported by our National Research and Education Network, ARNet. We also have close collaboration with our colleagues in Rian's, who have recently merged with NESI, our sister organisation in New Zealand. And I'm sure Yana will be giving us some updates on that. NCI handles the complete spectrum of science, pretty much with the exception of radio astronomy. The square kilometre array, as some of you heard about in one of the last presentations, which were using Rusio and FTS to transfer data to the different regional square kilometre array sites. So we do fundamental, strategic, applied, and industry-based research. So that's the normal things like physics, chemistry, and mathematics. Strategic is environmental, medical, geoscience, agriculture, materials. The applied is typically where my team spend a lot of time doing things like weather forecasting, We support the Copernicus program in Australia, which hosts around 6.75 petabytes of satellite data delivered by the European Union Copernicus program. We look at extreme weather forecasting, and today is kind of one of those typical weather forecast days. It's currently 42 degrees Celsius in Canberra, and pretty much down the eastern seaboard of Australia is experiencing temperatures greater than 35 degrees today. We also look at disaster management and mitigation, and work closely with the disaster response group in APAN. Industry-wise, we support a number of medical research institutes, particularly in the area of genomics, which I'll talk about a bit later. So our cloud system is called Niran. Niran comes from our First Nations Aboriginal Wiradjuri language and means the edge. Our Niran cloud is an infrastructure as a service capability, which is based on OpenStack, which allows us to deliver the edge case services, things like long-running data portals, rapid on-demand access to compute and storage resources, and doing a lot of the data processing, which supports our traditional high-performance computing workloads. Niran is used both internally by NCI for all of our data portal delivery services and our stakeholders to deliver things like long-running and web-facing services. Niran's been operating in its current form for around 5.5 years and replaced our previous offering, which was called Tension. And Niran was originally repurposed from our former Ryzen supercomputer. We had the challenge of converting a high-performance computing system to operate as an OpenStack-based cloud. This used 22 racks distributed across 2 data centers, with around 42,000 Sandy Bridge cores and around 1,400 Xenon Broadwell cores. We also tend to get all of the additional spare services or nodes, the other capabilities like our HPC team, which it doesn't really fit into our HPC platform. Things like Optane nodes, which are extremely large memory nodes. We operate around 60 petabytes of our own Ceph storage for cloud only, and this augments the 120 petabytes of large data storage, which is connected to both our cloud, Niran, and our HPC system, Gardi. This allows us to perform data processing or data service delivery or high-performance computing on the most appropriate platform, which is fit for purpose. Because the old Ryzen hardware was so old, we used a dispatchable compute model where we would power the nodes up in the morning to handle the load, and then power them down at night when the load decreased. As I mentioned, we do things like data collection, data analytics and dashboards, monitoring systems, service portals, data inflow and processing. As an example, we draw in about 20 terabytes of data per day continuously from the European Space Agency. We pull data from JAXA in Japan. And we have a number of other smaller data sources, things like the Australian Anglo Telescope, and a number of other instruments like our cryo-EM systems, genome sequences, and quite a variety of sensors and IoT devices operated by our partner organisations. We also operate a number of virtual laboratories and research environments, which allow researchers to use a graphical user interface to access NCI services via a web interface, so they don't need to install any additional tools or capabilities to take full advantage of NCI services. We also operate as a delivery platform for our stakeholders' cloud-based applications for some of the largest universities in Australia. And our infrastructure as a service offering allows our stakeholders to dynamically configure a collection of infrastructure, compute, storage, networks, and security, which can be scaled up and down to meet their requirements. Well, we extended the life of the old HPC system for over 10 years and 5 years in production. This has delivered a significant benefit for Australian taxpayers. However, the hardware is getting really old, and we've started to see a lot of failures happening, particularly on the mechanical components like disk drives and fans on the CPUs. Um, we were lucky to be allocated $1.25 million to replace the majority of the hardware around this time last year. And we went to market and replaced our existing capability with fifth generation AMD Turin 9005 series CPUs. We upgraded our 56 gig and 100 gig Ethernet to 200 gig. We compressed our footprint platform from 22 racks down to 2 racks, delivering a significant amount of power efficiency. However, the density of these is a significant increase in power and heat density. So we needed to do quite a bit of engineering to deliver the additional power and cooling requirements for the new system. Each of the AMD systems is a 2-socket, 64 processors each. Each socket has 64 cores and 128 threads, delivering 256 threads in each CPU chassis. We've got over 6 petabytes of Ceph, our mainline Ceph storage, and then around another petabyte of Ceph storage that we use for our internal infrastructure services. Our 2025 implementation of Nirin changed our control plane into a hyperconverged virtual infrastructure. That means we run the Ceph and the control plane across a number of nodes using an undercloud service. This gives us the flexibility to dynamically move around elements of the control plane, to segment the underlying control plane services into a development, test, and production environment. And because everything runs as a container, we're able to use a CI/CD pipeline to run from development through testing and then roll that out into production. So one of the unique capabilities that we've implemented in the last year is the use of a shared file system using CephFS to deliver volume and object-based storage. Where we're primarily using that for is to hold the virtual machine images that are running in the Nirin cluster. This allows us to live migrate services almost instantaneously. Previously, we needed to copy the underlying disk images between the nodes. By using a shared file system, the disk images are shared across all of the nodes, and all we need to do to migrate is to actually copy the memory footprint of the virtual machines which are running on each of the nodes. This dramatically improves the time that is visible to our users when we perform live migration, and allows us to take various compute elements offline as we need to perform maintenance, or if necessary, to compact the workload onto a smaller number of nodes during our 4 planned maintenance windows, where we would typically be doing power and cooling work in either of our 2 data centers. So we're able to flexibly move the workload around to the operational data center dynamically, meaning our downtime is significantly reduced now. As I mentioned, I've been away having surgery, so my team have been working on some really cool stuff while I've been off work for the last 2.5 months. One of the most emerging things is our Kubernetes environments. What we're seeing is a growing demand for Kubernetes-based environments. This is in order to reduce the dependencies on our ongoing OpenStack upgrade program. We decided to implement Kubernetes via Ansible playbooks within OpenStack projects rather than deploying the OpenStack Magnum container orchestration service. This provides a number of advantages that it allows development and CI/CD on team laptops, as well as on a variety of near and cloud environments, um, scaling different CPU architectures. So we still are operating some of the Sandy Bridge nodes. We're down to about 3 racks of those at the moment. But we use those as what we call our playground, which allows us to scale out Kubernetes environments and test the interaction between them in production, test, and development. It also provides a set of easy to deploy templates for Neuron users who wish to deploy Kubernetes services. And most importantly, allows us to perform intercloud migration of services if needed. This allows us to transport an environment, to one of the tier 2 institutional clusters if necessary, or into Amazon or one of the other hyperscaler environments, without having to re-engineer for the hyperscaler environment stack. So it's a fairly compatible and quite easy to use deployment methodology. Our deployment goals were spreading the availability of our Kubernetes node groups across multiple OpenStack services for resilience and redundancy, across both tier 1 and tier 2 capabilities for inter-institutional resilience and migration, and also to be able to cloud burst into hyperscaler environments when needed, in the cases where we would have to perform a major facility downtime to perform power or cooling engineering. We provide access to performance metrics and log analysis using a Grafana stack, both within the Kubernetes tenancies, and we have a global Grafana, Prometheus, InnoDB, Grafana stack that we use to monitor the operations of the service holistically across our own boundaries and across institutional boundaries. The Kubernetes system also automatically deploys OpenStack provisioning, resizing, and deletion of volumes, and uses our OpenStack S3 compatible endpoints. But because we've opted to use industry standards, we're also able to deploy those endpoints across tier 2 or hyperscaler cloud environments as well. Our initial implementation used mainstream Ubuntu as the operating system. However, we found that a bit too heavyweight for rapid CI/CD deployment. And we've switched to Talos Linux in the last 2.5 months. And we've been very satisfied with the operation of Talos as our underlying Kubernetes system. Talos provides an API managed service with declarative configuration using Helm charts. It provides extremely fast deployment of Kubernetes-based environments in a system-independent way. So if you're looking at actually dipping your toes in the Kubernetes environment, I'd really recommend you have a look at the Talos operating system. The link to their website is shown on this page. Some of the things we needed to do in terms of Kubernetes management, and I thought I'd share some of this with you, is we use a tool called K9S, which is a CLI-based Kubernetes management platform. This allows us to track real-time resources running in a cluster, perform log inspection, identify cluster metrics, look at multi-view resources, and much more. So for those of you who are command line aficionados, I'd strongly recommend using K9S to be able to debug and troubleshoot your Kubernetes-based environments. One of the things I've I'm really proud about my team delivering is the Guardians project. This is a national genomics project funded by Bioplatforms Australia, which is also being utilised by our Kiwi colleagues, Nessie, um, to run genomics services capabilities. Um, and I'll go into a bit of that now. So one of the key elements that we're providing is the foundational national infrastructure. So building data repositories for genomic services, um, supporting trust and identity management, supporting the ingest of large volumes of genomic data, and preparing that data for analysis on a variety of platforms, including our Guardi supercomputer and Illumina sequencer capabilities, which are an FPGA dedicated node for genomic analysis. We're kind of the foundational element of this, with other organisations in Australia acting as the end users, including our Australian National University National Centre for Indigenous Genomics. So some of the success criteria that we've been demonstrating today as our project deliverables: functional, secure, web-based data portal, stable accession identifiers for data sets, the capability of extracting detailed metadata from using standard ontologies to identify and search data, providing a hosting of national data sets following fair and care principles, but also ensuring that human data and personalized data is kept safe using ISO 27001 standards and other emerging personal genomic standards. Providing a convenient analysis on HPC and cloud, and a common analysis framework for HPC, supporting data access committees for each data set, and working on the documentation and training. And we've established legal and ethical guidelines for the way we do this work. So this slide kind of gives you a bit of an overview in terms of a researcher exploring, registering, requesting access, accessing, and then analysing particular genomic data using the GA4GH standards primarily. This is supported on our Open On Demand platform, which we call ARE, Australian Research Environments, using Globus for data transfer, Jupyter Notebooks for data analysis, Genotype Explorer for looking at genotype or genetic variants, looking at the C Bioportal capability for cancer genomics, and using IGV, JBrowse, and Chimera X as other graphical interface tools, which allow researchers to gain better insight of genomic data. Kind of looking at the big picture overview, we fit all of those services within the NCI capability, delivering it using our Niren cloud, and supporting a number of flagship cohorts, including Prospect, which is a program to support people with stage 4 cancer to be able to access personalised and emerging medical procedures and participate in new drug trials. So our Australian Research Environment, or ARE, is a web-based service created by the Ohio Supercomputer Centre using a capability called Open On Demand. It really lowers the barrier to entry of new users in being able to just access all of the supercomputer and cloud services using a single web interface from wherever they are, anywhere in the world. We're using Gen 3 as a data platform for building our data commons and data meshes. This was developed by University of Chicago. It's a set of open source software services that allow researchers to identify cohorts and particular variants or genetic expressions that they wish to research. Our implementation is a three-way PostgreSQL cluster, which provides point-in-time restore, auto failover, allows us to do rolling updates, has a built-in multi-node Elasticsearch cluster, uses OIDC and LDAP gateway for authentication, provides ingress creation and SSL certificate retrieval and renewal automatically, and provides a monitoring environment using Grafana and Prometheus. Our deployment, which I've duplicated that slide. Just one other point on there is that we're using Selenium, which is another open source package, to validate the interface operability and to run CI/CD capabilities within this environment. So that's kind of a brief overview of what we're doing at NCI at the moment. We're kind of dividing our time between the underlying infrastructure and then delivering some of the higher level capabilities which rely on it. In terms of APAN, over the last couple of days, I've seen quite a significant overlap between the AI and ML working group, or BOF, the Cloud Working Group, and the Asia Pacific Research Platform Working Group. There's a significant overlap in aspirations between the three working groups, and my observation is that the Cloud and APRP working groups have a significant range of technologies and experience, which the AI and ML working groups would significantly benefit from. So what I'd like to do in APAN62 in New Zealand, and perhaps before then with a number of virtual meetings, is to share some of our best practice to support the developing NRENs. Our Sri Lanka and Bangladesh colleagues are crying out for this capability, and share some of the technical expertise and infrastructure development that Japan, Australia, Singapore, and Thailand have already got working. So if I could pose a challenge to us that we start expanding our capabilities and support more working groups. So that's it for my presentation. I think I've probably gone a bit over time, so perhaps we'll have questions for the very end. So I'd like to now hand over to Keon Kim from KISTI, talk about research platform development for multi-domain issues. Thank you very much for your time.
Thank you.
And let me stop sharing and let somebody else get it. Thank you.
Yes, I want to ask you something later. Yeah, I want to ask something later.
Okay, not a problem.
Can you hear my voice?
Loud and clear, Keon.
Yeah. Can I start the presentation?
Yes, please.
Okay. Hello, everyone. My name is Kian Kim from KISTI. I operate the Korean AI research platform at KISTI, and I'm conducting research to advance the technology of this platform. Today, I will briefly explain our current platform and discuss the technologies planned for advancements this year. Let's proceed with the presentation. The table of contents consists of four parts. First, we will briefly explain the Korean AI research platform. And then last year, we changed the infrastructure and operating system of the Korean AI research platform. We will explain the changes, explain the current log collection process and the automation required for it. Finally, we will briefly explain the technologies being developed this year. Uh, the current AI research platform consists of 6 modules. The modules divided into login, Kubernetes cluster, image management, Kubeflow, uh, individual computing, SAP, and monitoring module. After logging in through the web interface, you can access two computing functions. The first provides individual computing for individual users, and the second provide a distributed computing environment for users performing large-scale jobs. To utilize these two functions, you can configure pods using images uploaded to Hover. You can also access images from other image repositories using web addresses. When configuring paths, uh, SEP is used for storage and is provided as an object storage platform. When provided as an object storage platform, data can be transferred between other clouds or servers using the S3 protocol. CoreaNet subscribe to Globus Online and can transfer data to the pods using GCP of Globus Online. The monitoring system monitors GPU, CPU, storage network, and so on by pod and by namespace. The graph you can currently viewing is a graph showing the status of the GPU through Grafana. And then the graph you can currently viewing shows the CPU, memory, disk and network information for the instance you are currently using through Grafana. The current AI research platform was developed for computing and aims to provide a web-based user interface for ease of use. The platform's core systems are all built using open source, and the container automation environment is established using Kubernetes and Containerd. For login, Cafe and Keycloak, developed by Keysti, are integrated the configure IAM. The storage environment is container-based using RUG and SAP linked to Kubernetes. Users are using Hover to store their own private images. Monitoring is implemented two ways. Users are using Prometheus and Grafana to monitor system resources, and the front-end LRC searching and Kibana will be used for log correction. Jupyter, Python, PyTorch, and TensorFlow are commonly used environment for AI research. Both web-based and CLI-based research environment are provided for these platforms. However, in some cases, when a web environment isn't available, only a CLI-based research environment is provided. Uh, Current users are mostly internal staff at the current center, primarily engaged in network-based AI research. Externally, they are also using it in NLP or research part. Next, we currently underwent a significant change in the infrastructure of the Korean AI research platform. The infrastructure used to provide previously provided most service using public IPs, and we have confirmed that many security issue arise when providing services using public IP. To address these issues, we strengthened security by incorporating firewalls and switch ACLs. We also configured a single access path for web services, allowing access to services created in Kubernetes only through the web server. And the IP addresses and the IP address of the server and the cluster IP address used for the Kubernetes cluster were configured to use private IPs. And the old OS was changed to the latest version. We also uh, we also conduct web service and server security vulnerability assessment. In the case, while infrastructure security has been significantly strengthened, there are still areas for further development. This will be addressed in future research. Currently, the Korean AI research platform is working to collect most error and warning from Kubernetes clusters. Uh, to achieve this, we are working to collect logs from all servers that make up the Kubernetes cluster and all paths created through Kubernetes. To this end, we are using Fluentd, Elasticsearch, and Kibana to collect logs. We utilize these three tools because they are conveniently configured to collect logs from Kubernetes containers. The collected logs are analyzed to determine the cause of the error and the nature of the problem. We then aim to develop a system that can automatically recover from the issues. The next area where our system is vulnerable is security for accessing internal services. Our current internal service security simply issues a token value when a service is created and then periodically updates the token value. However, this security method actually creates a problem. Anyone who knows the token value within a certain period can access the service by entering the address. To address this, we integrated three open source solutions: Kicklog, AOS2 proxy, and ISTIO with Kubernetes. This allows for centralized user management for multiple services created from Kubernetes. Also, to proxy automatically handles session management and token renewal. Furthermore, combining this with ISTIO's traffic management capabilities creates a robust security layer. To explain the functions of each component, Keycloak is an open source identity and access management solution uh, responsible for user authentication and authorization. Also, to proxy is a reverse proxy that uh, interconcept unauthenticated requests initiates the authentication process. The forward-only authenticated user requests to the backend services. It acts as a gateway between Keycloak and the backend services. ISTIO serves as a service mesh, providing traffic management, security policy enforcement, and observability. It receives external traffic through an ingress gateway and controls routing through a virtual service and gateway resources. The current AI research platform is divided into several dashboards. The Kubernetes Management Dashboard, SAP Dashboard, Prometheus Dashboard, and the Grafana Dashboard can be accessed from outside the platform via external addresses. Currently, each service has its own IP addresses. This fragmented management system presents some inconveniences, but the advantage is that it can be conveniently managed from a single management system and enhances external user access security. We plan to complete development within this year to ensure robust security. We also want to implement an environment where a problem with an errors and the rogues can be defined and automatically resolved through the collected law system. Thank you. This concludes my presentation. Thank you for listening.
Thank you, Kian. That was very cool. Let's keep questions to the end, but we'll come back to you on that if that's okay. Our next presenter is Xianwei from NSCC in China. Over to you, Xianwei.
Yeah, thanks, Andrew. Can you guys hear my voice?
Yep, coming through loud and clear. We can see your slides as well.
Okay. Yep. Thanks again. Yeah. It's an honor to give the presentation here. And instead of talking broadly of the distributed HPC in China, for today's talk, I'd like to introduce one specific technique to solve the distributed HPC issue. Basically, the slides are tailored from our recent SC paper presentation in last year. And it is titled as Container Compilation Assisted High Performance Computing Container Images with Enhanced Adaptability. Before going into the details, I'd like to first briefly introduce myself and also my affiliations. Just in case I'm new to you guys. I'm Xianwei, Associate Professor at Sun Yat-sen University. And before that, I was working in AMD. And before that, I got my PhD from University of Pittsburgh. And then currently, I'm working on the high performance and intelligent computing system. And about SYSU, it's a century-old university in Guangdong province, the southern China. It's pretty huge. And about our supercomputing center, it is NSCC GZ. GZ is Guangzhou. And it's famous for its two supercomputers. One is Tianhe 2, and the other one is Tianhe Xingyi. Yeah, both are being actively used. And let's step into the details. Because for nowadays, we have a very diverse high-performance computing systems. I mean, in terms of the hardware organization and also the system software and the environment. So it's very, very diverse. And in addition to that, we now have the cross-site integration. Dr. Moon just introduced the the project. We are in collaboration, the E3, and also in almost all in many countries, people are working on the to connect multi supercomputer computers in one single infrastructure to support our scientific and engineering projects, including China and US, and also the Korea and Japan. So in this case, for the cross-site integration, we are confronting one issue, that's the portability. So we can examine the HPC system and the environment to see why the issue happens. So here the figure shows the typical usage. So the system is composed of hardware components, and also we have some software stacks like the operating systems, the compilers, the libraries, all kinds of stuff. And there's one administrator to manage the hardware and the software. So means the system is shared, and with the management, the system can be opened for the users. The user just upload this file, application, and the data to use the system. So the problem is that if we have multiple systems of different configurations, then we may migrate our application, the source codes, across the systems. For this, each system can be of very different configurations. So in this case, it can be problematic. So it means when you migrate to a new system, you need to reconfigure. Otherwise, there can be two issues. One, that you cannot run your application, and the one that you can write, but it will be the performance will be very bad. And even for the single HPC center, we can also have the same issue, because each center maybe they have a multiple small clusters or multiple partitions, and each partition can be of a different configuration. So means we can very easily see the migration issue. And the problem just lies on the shared usage of the HPC system. So means, because we are sharing the environment, so means the software stack can be aging. So means you cannot very easily to upgrade the software stack like the OS kernel version. And also, the user has a very little control over the software stack. So because the stack is managed by the administrators. So in this case, we have the fragmented application ecosystem. So it also means we have to adapt to the system. Means we will be in trouble of a vendor lock-in. So means you cannot very easily switch to other vendors or other systems. So it will further cause the poor computation reproducibility. So means you cannot very easily to reproduce the computation finished by someone else. And the one emerging solution is the container from the cloud computing. So with container, we can create the general image, and then we can run the image on different systems. And the container is initially used for the cloud computing for convenience, but for the high performance, it's just a new thing. And people are actually exploring the container for the HPC, like the Charlie Cloud or Shifter. So the container can help to hide the heterogeneous, the difference among the systems. But still, the container will, it cannot, or it will suffer from the adaptability issue. So means not everything can be portable. So we just cut into 3 layers. For the layer like the hardware and the kernel, it is always fixed. So means you cannot adapt, or you cannot migrate. You cannot control it very easily. And for the application and system software, it is target related. So means different systems, they will have different versions or different configurations of such software stack. And for the user level, it can be very easily to be ported. So the issue are in detail, it means the authors, the image authors, they typically don't know which platform the image will be deployed. So it means the performance will be a disaster. And even the authors know which platform will be used. It's very impractical to optimize for every HPC system. So that's the issue, the performance issue. And here is a motivation study for the Lulash, one very typical high-performance application running on the ARM-based high-performance cluster. And the top bar is the generic image. So it means we just create a very general image to be portable across systems. And the bottom the bar is the native build. So it means we just build for the specific system configuration. So you can see the difference. I mean, the cost is the execution time. We can see that for the generic, the time is very long. And for the native build, the red part, it is significantly reduced the time. And we can see the contributors or the factors once the system-specific libraries, it is of a very huge impact. And also the system-specific compiler toolchains. And also the advanced optimization like the LTO, link time optimization, and the performance-guided optimization. So it means without those optimizations, we cannot have a very high performance. So the conclusion that generic images are portable but not adaptable or not of a high performance. So it's not acceptable to the HPC users. So our idea is that we should do something. So we should introduce additional build time source data into the container image. So it means we will enrich the image with actual information to enhance their adaptability and reduce the target dependency. The idea is just like what the figure shows. So it means, yeah, for the source code, we will do something to have an extended layer of the image, and then we can adapt it to multiple systems. So the sub-goals are of 3 levels. Yeah, first, define a common build environment, and then the image should be compatible with the standard. And the final one is that we should enable system-specific adaptation and optimization for performance. And I'll talk about the design implementation. The general workflow is just like this. So we will intercept the normal image creation process. We will analyze the building process and then capture the information and save into the actual layer. And when we know which target system will be used, we just rebuild the process. So it means we will recompile the source code and apply all kinds of system-related optimizations to have a high performance. And there are 2 sides, user side and the server side. For user side, yeah, this one is the normal image building workflow. So you just create the image in 2 stages. And for our design, we will do something else. Yeah, just like the bottom figure shows. Yeah, just as I mentioned, we should first analyze the building process and get the information and then save into the extended layer. So just the 2 actual steps, analyze and then cache, just keep the actual information. And then we can have the enriched image to be used on the system side. On the system side, yeah, this is the normal process. And here is our improved process. So we will rebuild and redirect the image to have a high performance. So just rebuild and redirect. And here is the container workflow. Well, yeah, container just means the mix of a compiler and the container. The container. I will skip the details. It's just multiple modules. And here's the core part, the intermediate representation. And for the evaluation, yeah, we evaluate on 2 HPC clusters. One is x86 and the other one is ARM, each with 16 nodes. And we test our representative high performance benchmarks and real applications. And we just report the performance and the image size to gauge the effectiveness of our design. Yeah, here's the performance results on the x86 cluster. And the original is just the generic image. Native is somehow the upper bound. So it means we just create the image for the specific configuration. And adapted and optimized are our designs. The difference that optimized we will apply some very deep level optimizations. Adapted just without such deep level optimizations. And here we can take a closer look at the performance. We can see that we can significantly boost the performance compared to the original images. And also, the performance is very close to the native one. And with further optimization like the LTO and the PGO, we can further improve the performance. So the performance can be even higher than that of a natively building process. And here's the results on the ARM clusters. Generally, the trends are pretty similar. So it means our design are very effective to improve, to mitigate the performance loss, and even gain actual performance opportunities. I'll skip this slide. And for the image size, actually, the overhead is very small compared to the whole images. So it's very small fraction. And just to conclude, our work is trying to solve the adaptability issue in the distributed HPC system, because the issue will cause the performance loss of containers in diverse HPC systems. And our solution is container. It's a compilation assisted HPC containers. We just introduce additional build time data into the images to mitigate the performance loss. And also we apply system-specific adaptations and optimization to bring the performance up close and even higher than that of a native level. And for the future work, first we are actively extending the container to support the portability. So it means we can run the image across very different systems. This one we call it a cumulator. It's a compiler plus emulator. It will be published very soon. And even before, in addition, we are also trying to apply those techniques into our systems. GCC, the Creative Cloud. It will be used as an info for scientific exploration and practical uses. So hopefully next time, we'll talk about our product. So the techniques will be used in this product. Okay, that's pretty much of my talk. Thank you.
Thank you. That's really going to be beneficial to a lot of us who have quite heterogeneous compute environments of various vintages. Excellent work. Really looking forward to trying out your compiler emulator.
Okay, thanks.
We'll push questions further out. If I could now hand over to Yana from Rianne's.
Hello. Thank you. I will just share my screen. Oops. And please let me know if you are able to see my slides. Good. All right. Hello, kia ora. My name is Jana Makar. I am from Auckland, New Zealand, and similar to Andrew, I just wanted to extend my apologies for not being able to join you there in person. This is my first APAN conference, so I was very keen to experience it for the first time there with you, but I will have to save that for later this year, and I hope that you will join us in New Zealand in August when we host APAN62. And again, to continue a lot of these conversations and start some new ones. I'm honored to be part of this session. I kind of want to say that now is time for something a bit different. I do appreciate the technical talks and the deep dives that we've had in the previous talks. looking at some of the HPC platforms and the capabilities and power behind these collaborations and combinations of software and networks and AI and compute. Because I think that leads in well to my talk, where I want to speak a bit about the importance of us sharing these stories and the things that we are enabling with our infrastructures and with our setups and our solutions to these challenges. It's really important to share these stories not only here in this conference and in this event, but beyond as well. So my name, again, is Jana Makar. I'm the communications manager with RIANS. And as Andrew alluded to, we have, as an organization, evolved our services and capabilities quite a bit within the last year, and I'll explain that a little more in this presentation. But yeah, I come from a comms and marketing side of an HPC background, so I am familiar with some of what you're speaking about, and again, a big proponent of sharing these stories beyond so that everyone can come to appreciate it. So I did want to sort of start with a bit of context setting in terms of why do we want to communicate and talk about the things that we are enabling. We know as a community that the work we do is important and valuable, but not everyone out there might have the same awareness or understanding. And that could be because they aren't in our circles, they're not in this event right now, they won't have a chance to see our presentations, or they might be aware of us, but they may not quite understand what we do. A lot of the projects that we're working on and the solutions that we're delivering are very technical, they're very complex. And so depending on the audience you're talking to, that might be lost on them. They may not understand the what is actually being achieved. So my talk wanted to look at the value of why we want to tell our stories, share this impact, and communicate the importance of what we're doing, because it can help bring along other members of the community and the audiences that we're speaking to. We can bring them along and help them understand, and so that not only lets them appreciate the work we do, but getting down to it, continue to fund us as well, and invest in our infrastructures and let us continue our work. When we bring people along on that journey, that can mean a couple of different things. It could be attracting new users or researchers to come onto our platforms and choose us to power their work and their projects. It can also open doors to new collaborations. I really liked in the last presentation, I mean, there's collaborations and multi-institutional and across multiple countries. That's the nature of science and education and innovation these days. So we want to be part of those collaborations. When we talk about what we do, we also have the opportunity to listen to and respond to the needs of our stakeholder communities. So whether it is the IT teams at various research institutions or the researchers themselves that rely on this infrastructure to power their projects, we can understand, what will help them be more efficient and get results and publish their findings and share those discoveries more quickly and easy. And if we can communicate that, then again, going back to being funded and invested, we can show governments and partners and other investors that it is worthwhile and important to continue to have sustainable digital infrastructures in our countries and our regions. So yeah, in terms of the value of communications and engagement, it really is building that awareness and turning that awareness into recognition. And from recognition, we can get continued support. So the other values of why do we want to connect infrastructure and the work that we're doing to real world impacts? Visibility really does matter. A lot of the infrastructure and resources that we are working on, it's behind the scenes, networks, data centers, technical expertise that's happening in the background often. And I think that we need to make sure that we are bringing those from behind the scenes and raising that visibility so that what we do, the people and the kit and the equipment and the tools, the software, are recognized as essential infrastructure and real enablers of progress and innovation. Also, all the work that we're supporting, it does have everyday impacts. We can follow the connections of a lot of the research and that we are powering and supporting, and it is having delivering benefits and outcomes in areas of health, in the environment, climate, industry, and then also unique regional or local priorities. The images on this slide along the top are just a few examples of some of the case studies that RIAN's services and capabilities are supporting. And so whether it's researchers that are studying the movements of infants to better diagnose neurological disorders, or researchers that are modeling flood mitigation tactics and approaches, because every year now we're getting a 1 in 100 year weather event that is, we need to be able to react and adapt to. Or there's better understanding our indigenous species. That last photo is an indigenous parrot called a kakapo. And we're sequencing the genome so that we can help preserve that species, because it is on the very brink of being endangered and extinct. So again, we are supporters of innovation. That is very, very important and critical to maintain, because we're responding and helping our users and our customers respond to the demands of modern research and education. If you want to see more examples of case studies, the link at the bottom there takes you to our website where we share some of those stories. And so here is RIAN's. We are part of the wider global NREN community. We're down at the bottom of the world, but we are part of the wider landscape, and I've come to learn more about the GREN, and I really appreciate the community aspect of it and the collaboration that happens across and between all of the NRENs. As mentioned, we've had a busy year. We have evolved as an organization. We are a Crown-owned membership organization, but we are really now a unified and centralized e-research platform. So beyond network services and expertise, we now have brought over a national high-performance computing capability and platform that includes not only resources and infrastructure, but staff and expertise that help researchers build capabilities through training. We offer consultancy to have research teams build capability and be able to use our resources more efficiently and adopt sustainable, fair and practices and computational skills. And we have data services as well, in terms of using tools like Globus to enable large data set transfers. So on the left is a few of the network services and connections that RIAN's offered, and then with our integration with New Zealand eScience infrastructure, the HPC platform and providers, this is now our wider scope of focus and capabilities. So really a rich array of different types of services that we can offer. So in terms of communications and engagement and sharing the value of this wider suite of capabilities, we have audiences that are similar but different. Historically, I came from the NESI side, so the New Zealand eScience infrastructure, from the HPC platform. I came across, and historically, we would focus on researchers and research teams. Those were the ones who were accessing the clusters and running their codes and working with us to use up as many core hours and GPUs as we would give them. And that was our audience, and that was sort of our core focus. And now that we have integrated and moved into sort of the NREN landscape, we now have audiences of IT teams and network engineers, and both of these sort of groups definitely have different audiences at sort of a layer layer cake of levels. We have the end users, we have managers and decision makers who are deciding whether to become members of REANS or fund projects to have the financial ability to buy core hours and buy time on our systems. And then we also have an audience of the funders, whether that be government or other members that are acting as investors and contributing to the investment of our infrastructure. So all of these audiences need to be able to hear this communications and this value story, but we need to tell it a bit differently for each of them. So recognizing that, and it is sort of maybe the same story, but told in a different way. In that sense, a lot of the core communications and engagement tactics that we used as NESI, we have brought over to REANS because we found that they've been really useful in terms of ensuring that we can share that story, we can communicate the outcomes, and we can raise that awareness and understanding of the value that our infrastructure and our people are delivering. So again, we aim to have our stories be user-focused, community-driven. The things that we do to support that include sharing those outcomes and success stories. So if we've enabled a research team to produce a publication, that's an outcome. If we have enabled a team to build in network resiliency, that's a positive outcome. If we have brought together people at an event that is, we want to find these different ways to share the different aspects of the work that we do. User experience is often a key source of where we're finding that content and where we can share those positive stories. You always want to celebrate positive user experiences, and especially ones where maybe you have done some work to improve an experience because it wasn't so positive. It does show to your stakeholders that you are listening again to their needs and responding to them. The other key and sort of core element that we really try to work into our communications and engagement tactics is consistent messaging. So that means empowering different voices across the organization to share our stories and using consistent messaging as well if there is a particular narrative that we want to get across. So that can be done through different people presenting at different events, using templates for things so that people have guides and guidelines around how they can use the key messages and work them into the stories that they're telling. Examples of the ways that and some of the tools that we're using to do this comms, to do our comms and engagement is case studies. I've got some images on the slides here of our website. We have a section where we publish case studies similar to the ones that I shared on the slide previously, showing either the research that we're supporting or the ways that we have made things easier and faster and improved the processes for research teams and users on our systems. We varied these as well in terms of our audiences. Some of them are quite short and use very plain language and high-level type perspectives, and others get quite technical, especially for ones related to our consultancy service, where we have research software engineers embedded and working directly with project teams. We have them share their learnings and share that process of the technical expertise that they've contributed, because we know there's audiences out there that want to get into those technical details. We have different newsletters that we will share and contribute to. REANS itself has we call it more of a broader community newsletter that goes out to a wide group of stakeholders, and it'll share general updates or larger scale organizational news. But we also have a very focused training newsletter. So that is includes content that's specific to researchers and research community members who want to build their skills or deliver training, which we want to collaborate with them on. And then now, newly joined to the NREN community, I really want to see if I can get some stories published in the field, which is the GREN Zone sort of newsletter and website and platform for sharing these stories. So looking for opportunities to either include success stories and communications within your own channels, but leveraging partner channels as well is a great tactic. In reporting, I've got a photo there of, annual reports or any sort of metrics or year-end statistics that you can share about how many those charts and graphs that some of the earlier presenters were sharing of usage times and speeds and capacity of the systems. Sharing that in terms of usage is always really a good way to demonstrate that your systems are full, that they're active, and that they're being relied upon by the research community. And last, running events and giving presentations, and especially collaborating with your partners to give those presentations so that they can share the stories on your behalf, have all been really, really good tactics. And so in this sense, because I'm new to the community, I'm curious and I want to connect with others, definitely want to hear how other people are doing this. And if you have questions, and I know that there's opportunities to collaborate on things, and when there are multi-institutional collaborations happening or across the NRENs, let's help each other to tell our stories and support each other. But that is the end of my talk, and I am putting my email address up there to connect with anyone who does want to talk more about communications and engagement strategies, whether it's for the HPC side of your organizations or the network side. Now that Rian's covers all of it, we are always looking for inspiration or ideas that have worked well at other organizations. So please get in touch if you'd like to talk more. Thanks very much.
Thank you for an excellent presentation, Jana. You'll be hearing from some of our NCI comms people shortly, I hope. Okay, let's pass on to our last speaker for this session, Verochai from Tyren NII. Chai will be presenting on forest and AI. This will kind of directly...
Usenet as well now.
Okay, he's a man of many talents. Jana, this is going to be a really great presentation on the deliverables and outcome of actually using some of these services and capabilities for national good.
Yeah.
Over to you, Chai.
Okay, thank you, Andrew. This is just the work that we have done, combining from the open and sharing working group and disaster mitigation with the previous work that we work with NASA and NOAA. Then now it's in oh no, I do it. It's fine. In the operation for the national park and then the Royal Forest Department and some NGO in the country. Okay. So it's just the part. The prevention and communication is the one that really need to do. As Jana said, that very important, the most important when you deal with the disaster. So this we just the update that we used to use the information from NASA, but now changing to get it faster from NOAA. So NASA used to be 1.5 hours or 2 hours for us to get the data from the satellite when it's overpassed in the region, Upper ASEAN. But now we can have that they have some kind of technology that I don't know that they can process very, very big satellite data up in the satellite itself and send it. So now we can get information around 35 to 40 minutes after the satellite overpassed Upper ASEAN. So just see, this is just a typical thing, but can go over. But the garbage in, garbage out, it doesn't matter. You have, whatever you do, you need a very good data. That's why we're trying to push very hard on the open and sharing data, and then toward the open science, which is another session, and we have discussed a lot about that, even the AI ethic with UNESCO core data, RDA, and that's just the message. I try to get it quick because we are over time. But this is traditional monitoring is one of the 7 things that we usually do when we are dealing with disaster. Monitoring and detection is the 3rd. Prevention, and then the communication is the 1st thing. And we all agree in the world now for the suppression, the response process, it costs too much. So you have to put all the money into the prevention and communication to deliver the message. Typical 5 years ago, well, maybe, yeah, like 5-6 years ago, we have the official letter to NOAA, so we can get the data directly to from their server. Then we have this is Winfred Schroeder and Davita Street, that approximately 40, someday 30 minutes we can get data, and they all move their satellite products from the small server. Now we are in the big U.S. Forest Service that NOAA provides for the fire suppression operation in the U.S. So we are safe. So it's in from NASDIS. I got the 2 years ago, 3 students from France, computer engineering, writing code to present because we only get the email address. Email alert. And then last year, 2 more, also from computer engineering master degree, they write the code to improve it to be much easier for the users that we talk with them and then fix it. So we use 5 master degree students to do this, to make it simple. Just it's very difficult if you want to make it simple, because different agency, they request different things, so you have to talk with them and do this. So we have this for Thailand, and it looks like this, just simple. You have the information as soon as possible, display in the particular boundary that you need, and then you can link it to the Google Map. Then you can use the direction and go to that particular active file location. So, but the layer on the left is different. In Thailand, in Laos, Cambodia, and Vietnam, they are different because they are different mandate, the problems. So this is just the example. This the page for Thailand, and this is operation that they're using in the command center, operation center. This is example from the Royal Forest Department, and then this is example from Cambodia. This was Laos, and this from Vietnam. So we have 4 forest departments that we work with. But Laos will use it in operation hopefully soon, because they just found that the suppression unit, Forest Fire Control Division in Laos Forest Service. But this is just some would like to get the text. They don't want to use the map, so I don't know. It's just extract and then report. And this year, the Department of National Park use it in the war room that they established 14 war rooms throughout the country, so of Thailand. And then Royal Forest Department already use it, and some NGO they use it also, because we go down to the local administration.
Stop the connection. Yeah.
We seem to have lost your audio, Chai.
ago, actually, 2004, but we don't have any budget. All of these are free. That's why we need take time. And then last year, the professor in Chulalongkorn University in the AI department, he's trying to help, but the result is not that good yet. So this based on the free time, so take time. And yeah, I think that's it. That's just a final words that climate change. So we have to work together, and then working together, support each other, like open and sharing data, trying to connect people together. The disaster mitigation workshop, which happened at the same time, also talking about the how they're doing to help the people before, during the disaster, and after. And the last one that hit hard, cyclone. That's why we are talking at the moment right now, but I couldn't be there. But because of the hit from start from Philippines and then well, a bit from Philippines, hit Malaysia very hard, but very bad in Sumatra and very, very bad in Sri Lanka. So we try to talk how because of the Philippines, they have like 15 category 4, category 5 typhoon hitting all the time. So we try to discuss how to get the way they're doing it for the other country, because they have very good experience. Thank you very much. I think that's all. Yeah. So see, many training, many things that I have been through to try to get them work together, even the army, and then with the U.S. Yeah, U.S. Army. This with the Korean. This is with the Korean and the French, civil protection. Just try to get them together and then work on the separate issue. So they work same thing. So I said, well, help each other, and then the South Korean and now South Korean and the France and Thailand are working together for the fire suppression training with the Korean technique, with the French technique, with Thai technique, try to help different like 15 countries to improve the way they're doing it. Thank you.
Thanks, Chai. That was really great. Let's open the floor up to any questions that people have.
Were there any questions about the whole sessions?
Jong-Hun, did you have a question?
So you said about the Ansible. So I have a couple of questions about the Ansible and some of the intercloud migration. And one question is about the Talus. So my first question is, why Ansible over Kubernetes native tools? What was the biggest operational challenge? And another one, how is intercloud migration handled at Kubernetes level? Do you rely mainly on Kubernetes abstraction or cloud-specific tooling? The other one is like, since Talus removes SSH and is fully API-driven, how do you handle debugging and incident response in production?
Okay, I can probably answer a couple of those, but maybe not all of them. The reason we chose Ansible was mainly because of the around 10 years of technical debt that we hold. We've used multiple implementation platforms, including Puppet. We use Ansible for the deployment and then Helm charts within the Kubernetes environment. Ansible's kind of more of a kind of personal choice that some of our team members made, but we've found that it's easily deployable across a number of cloud platforms. We have looked at other implementation capabilities as well, but Ansible's just where we've done the work. So we're happy to share any of those Ansible playbooks. It's more just that we have capabilities to support Ansible within our team. There's no kind of hard and fast. Terraform was the other one I was looking at. We do have some users who've migrated to Terraform, once again using Helm charts within those Kubernetes environments. So it just really depends on how old your team is, and kind of what their expertise and skills are in particular areas. In terms of inter-cloud migration, the instantiation of an environment's usually pretty easy. The biggest challenge we face is how do we move data around in a coherent way so it is available when we actually need to compute against it in either any of those environments. What we've been trying to protect against is a natural disaster, which would take one of the two tier one facilities offline in Australia, where we have mission critical data, things like the bushfire monitoring systems that Chai mentioned, that Australia also has, and that we can respond to natural disasters by potentially offshoring some of those services if it's absolutely necessary. But yeah, we try to provide the maximum level of flexibility that we can without tying people down to particular platforms or services or methodologies. So yeah, it's kind of a bit of a moving feast, and we kind of tend to churn technology over a kind of 3 to 5 year period.
Thank you, Professor. About Talos, you didn't mention that answer of that.
To my knowledge, I haven't actually played with Talos. It's one of my team members who came up with it. We're actually spinning up a Ubuntu or a CentOS image within the container tenancy, where we run things like K9S against it to actually monitor the operation. But one of the things that we've found is, well, let me just wind back here. My team has the old Unix geeks. So all of us are used to playing on the command line and using SSH. And one of the things that I've been really keen is to make sure that we can't just pop into that environment and make an unscheduled change, that we actually force the CI/CD pipeline and make that happen. It's very tempting just to SSH into the box and just make that small change to make it work, and then forget to actually implement that in the GitHub. So it's more just a process-driven thing that means that you can't easily do it. So it encourages people to do things the right way rather than take shortcuts.
Thank you so much, Professor. Thank you.
Thank you, Andrew. Yes, my question is almost similar. Is Talos is worth it, even though for distributed environment?
We've had really good results with it. We've only been using it for about 3 to 4 months. But the thing we've noticed is our deployment time's gone from around 2 hours down to about 21 minutes in the latest build using Talos. So it just seems a lot faster and a lot smaller in terms of deploying those environments, and a lot lighter weight. And to Jianhui's presentation, just maintaining that balance between an optimized system-specific version of something versus the generic "it will run anywhere" version. We really, one of the things that we're all aiming for in our HPC and network environments is energy efficiency. We don't want to burn the planet. If we can save a watt of energy anywhere along that process, it is advantageous. We have limitations in terms of our energy generation capability across many of our APAN countries. So trying to make it the most efficient we can is benefiting the whole of the world.
Thank you. And China, thank you for joining and sharing your experience and the contents. And I hope that they see you at the New Zealand next APAN meeting. Thank you.
Thank you.
Yeah.
Do we have any other questions?
Yes, I have one more question. Sorry for that. Professor from Professor Jianhui Zhang from China. Okay.
I think he may have left us, so maybe if you could drop him an email with your question.
Okay.
The second week of this February, next month, February second week, and the A3 site workshop held at the KISTI.
Yes, Professor.
You joined the KISTI and you met. You will meet. It's a sharing focus.
Thank you, Professor. It will be my pleasure.
I will let you know this the moment detailed information.
Thank you, Professor. Thank you so much. Thank you all.
Okay. Thanks.